Okay, so today is the last lecture. So I was planning to just basically discuss the charges in gravity, in asymptotically flat spacetimes, and then put into use everything that we learned so far to basically derive from scratch the soft gravitons theorem from a conservation law associated to the asymptotic charges. So last time we discussed a little bit, well, not a little bit, a bit more these ideas in gauge theories. And we talked about basically large gauge charges, but I didn't really tell you how to construct those. So today I'm going to just discuss, in the first lecture, I'm going to show a general method of constructing these charges. So it goes under the name of covariant phase space. And then with that understanding, we're going to basically apply it to gravity in four-dimensional asymptotically flat spacetimes. So the general idea here is to consider spacetime manifold M and a field space F So usually we can think about fields as basically a jet bundle over this spacetime manifold M. So here for field space, we usually have a collection of fields phi I together with their derivatives and so on and so forth. And we can think about the situation in this way. So at every space-time point, we have a fiber where the fields live. So you can think about this as field space. And then, so the total space, so locally we have basically F times M, and the total space is this vibration over the base space, over the space-time. And so we can also consider sections where you take representatives from the fibers and evaluate them at particular space-time, over at different points in space-time. So this is sort of the picture, and it's a standard thing that you would be doing, for example, in classical mechanics, maybe just written in a bit of a different language. But I think it's useful because you're going to now introduce basically exterior derivatives on F and on M, and it's important to distinguish between those two. So, okay, so this together is like a jet bundle. So, now, with this picture, there are two things that we can do. So first of all, so you may recall that the on M, we can define the exterior derivative. So there is a theorem complex where you go from basically the collection of zero forms, so functions on M, to one forms on M, and so on. The maximum dimension of the form that you can have is the dimension of M, right? So for example, for n-dimensional manifolds, you can have at most n-dimensional forms. So those would be top forms. But in between, you have collections of various different kinds of forms. And to go from the space of, for example, functions to the space of one forms, you can apply this exterior derivative d. So this d, in this case, is basically d by dx mu, and then we can have d mu plus d phi I dx mu d phi I, and so on and so forth. So this is an explicit coordinate expression for this exterior derivative d. And then the other thing that you can have is an exterior derivative on f. So Here we have, again, we can also define 0 forms, 1 forms, and so on and so forth on field space. And the exterior derivative I'm going to denote here by this delta instead to distinguish it from the space-time exterior derivative. And this delta explicitly is given by delta phi I d by d phi I plus delta phi I. So I'm going to, sorry, just for simplicity, this d by d mu phi I, I'm going to just define it to be phi I mu and so on. D by d phi mu. Okay, and yeah, and again, just like this exterior, the usual exterior derivative maps you from like n forms to n plus 1 forms. The exterior derivative on field space maps you from n forms on field space to n plus 1 forms on field space. So these are, so A is exterior derivative on M, and then B is exterior derivative on F. And we can also define interior derivatives. So you can also go down this chain by basically contracting, by applying this interior sort of derivative or interior product. So where this interior product is, you can think about it as basically this K form eating a vector field and giving rise to an n minus 1 form. So it's like psi mu d by d, something like this. Okay, so the idea is that now on this net, on this total space of this bundle, we can have basically PQ forms where for the first entry here is gonna be the form with respect to space-time. So basically we have P dx mu's and Q delta phi. So it's a P form in space-time and a Q form on field space, right? So for every quantity that we can write down is going to be such a P comma Q form. So now what we're going to do is to basically just recast the usual Noether prescription in this language and also generalize that to construct basically like asymptotic charges in both theories of gravity and in gauge theories. So now let's recall that, so we're always going to work with Lagrangian theories here. So of course, gravity is such an example, and you usually are going to work with the Einstein-Hilbert action, but of course you can do this procedure for other theories of gravity as well. So we have a Lagrangian, so given a Lagrangian theory, the action, as you know, is the integral over the space-time of the Lagrangian. However, we can basically reformulate this. So usually the Lagrangian, right, is a scalar. It's a function of the fields, right? Function on field space. It's a function on really this jet bundle. But I can also write it as an integral over the space-time manifold of a Lagrangian n form. D form. So D is the dimension of M of the space-time. And it's obtained, of course, the two are related via the Hodge dual. Yeah? So it's going to turn out to be a lot easier to work with this Lagrangian D form as opposed to the Lagrangian. I mean, of course, the two pictures are equivalent. You just have to like uh, well, be a little bit more careful in terms of like what the quantities are that you are working with when you do it like you would usually learn in classical mechanics. It's a bit cleaner to do it in this way because you know exactly what kind of object in terms of this jet bundle picture you work with. So let's do the latter version. Maybe it's not so familiar, but again, as an exercise, you can just go back and sort of like rederive your Noether theorem, basically, like relate what I'm going to do now to the usual thing that you may be more familiar with. So this Lagrangian D form is a function of the field. And it is, in this notation, a D, 0 form. Right? We don't have usually, there are no deltas in here, right? It's just a function on the on this jet bundle. So then the variation, so usually when we think about symmetries, we consider the variation of the Lagrangian on field space. So usually we write down something like delta L, then we vary it and look for transformations that preserve the Lagrangian. But in general, taking the exterior derivative of this, the exterior derivative note is on field space of this Lagrangian D form on M produces a D, 1 form, right? So I'm good to take this. Of course, if I were to take space-time D on L, that would give me 0 because it's a top form on space-time. So this gives me the thing that you usually get. So we have just the variation with respect to each of the field coordinates, to coordinates on the field space, delta phi I. Yeah, so this is the standard thing. And then now you may also recall that by studying this variation of the Lagrangian, we can usually also recover the equations of motion up to a boundary term, right? This is what you usually do when you derive the Euler-Lagrange equations. You look for a stationary point in the variation of the action. So in general, this can be recast as some. Here now, this is going to be a D form in space-time. The equations of motion, you can think about them as Hodge star times the usual functions that give you the equations of motion times delta phi I. Well, roughly speaking. So here, if you have more things, okay, it's going to be you're going to get a collection of equations for varying with respect to each of the individual fields on which the Lagrangian can depend. So I'm going to schematically denote it by this. And in particular, the key thing here is that on shell, this first term will always vanish. But then what is maybe sometimes less talked about is the fact that, of course, when you vary the Lagrangian to put it into the usual Euler-Lagrange form, you always have to do some integration by parts in over M in space-time. And usually we assume that fields fall off fast enough at infinity and that all of these boundary terms vanish. But that's not going to be the case for the problems that we're going to be interested in. So let's keep track of that. So usually we have some some D acting on some object that I'm going to call theta. That's going to now be a function null of the delta phi's as well as the phi's. So this is the d comma 1 form on B. This tells me that basically this theta has to be a d minus 1 comma 1 form on B. Okay, and the theta is called the presymplectic potential. It's going to play an important role in what we're going to do next. And yeah, it depends on the fields and the variation of the fields, but it doesn't explicitly depend on the coordinates. Okay. Now, let me write it here. So given this theta, I can define a two-form on field space by taking the exterior derivative on field space of this theta. Yeah, so I can always construct so this is a d minus 1 comma 2 form, and essentially, as you know, phase space is from classical mechanics is an even dimensional symplectic manifold, and really what this omega is the associated symplectic form on that manifold. So you can check that it has all required properties. It's a really, I should have said it's a pre-symplectic form because you also want to impose that this is non-degenerate. So then you also have to do that to obtain the symplectic form. But let me not go into these details right now. So so now with this sort of preliminaries in place, we can construct so-called Noether-Wald charges. I'm going to review how that goes in a moment. And furthermore, prove something that now goes under the name of the fundamental theorem of covariant phase space. Which tells us that essentially locally that we can write this the symplectic form. So what does this tell us? It tells us that given a vector field zeta, like the ones we discussed before, that generates asymptotic symmetries. So we're going to discuss a bit more how to derive these vector fields in space-time in the second lecture. But let's say we have such like essentially asymptotic symmetries, or sort of in gauge theories would be like the large gauge symmetries that we discussed, large gauge transformations that we discussed last time. So given such a vector field, then we can define d minus 2 form in space-time, kappa, that's parametrized by this vector field, whose exterior derivative on M is basically that symplectic form, but now evaluated at a variation of phi. Oh. On shell. So I'm gonna sketch how to. It's actually not that difficult to show. Let me give some references actually for this. So first of all, these kind of ideas, reformulating this whole thing in this form language, has appeared in papers by Wald and collaborators. So Wald, Zupas, Ayer, maybe I'm missing another one from the early 90s. So you can look these up. And then a nice review of all of these ideas, including a proof of this fact here, is also given in Geoffrey compares advanced notes on general relativity. Okay, so you can read about this there, but let me just now kind of sketch what we actually will need for to write down the charges in a series of gravity, so associated with vector fields with asymptotic symmetries generated by psi. So first, so the plan now is to basically discuss how to obtain this Q zetas here, and also how to construct this little k zeta. There's going to be a formula for this space-time d minus 2 form expressed in terms of these q zetas and the symplectic potential. So this is what we are going to do now. So to do that, it's very convenient. We're going to often use, so, sorry, and I should also say that you see, like, while this delta is a generic exterior derivative on field space, this delta zeta does not bring me up on this, it's just the Lie derivative. Of phi on field space with respect to zeta. Okay, so it does not, the Lie derivative doesn't change the degree of the form. So to show sort of some useful identities, there is really just one, is this Cartan formula for the Lie derivative of generic forms. So the action on a form can be written as exterior derivative on space-time, interior derivative with respect to zeta acting on the form, plus the other way around, interior derivative with respect to zeta, d acting on the form. And the way to prove this, so it's called Cartan. I think it's in the literature somehow it's called Cartan magic formula, but that's a bit silly, so I'm just going to call it Cartan formula. I mean, there isn't that much magic about it. So yeah, so basically you can prove it recursively by starting with the action of the, basically checking the formula on functions and then sort of proving it by induction for n forms. So on functions, let's take this, formula, and this tells me that this should be this plus this, so derivative, exterior derivative, interior product on f plus interior product, exterior derivative on f. But we just saw that the interior product takes us from k forms to k minus 1 forms. Obviously, f is lowest degree, a 0 degree form, so the interior product on it has to vanish, right? The space of -1 forms is empty. So we just have that this thing. And what is that? Well, it's just, can write it in coordinate notation. So this is interior product with zeta d mu f d by d mu. This is just d of f. And the interior product basically eats this bit and contracts this with zeta. So we get zeta mu d mu f, which is exactly what the definition is of the Lie derivative acting on functions. So this is okay. So yeah, so basically assume that it holds for k forms and show that it also holds for k plus 1 forms. So you have checked the induction, the basic induction step, and then you would do it like this. Yeah. What are you? Because this delta is exterior derivative on field space, but as you can see from this formula, this is this doesn't change the degree of the like, because where exactly are you asking? Here? Because the omega here, we're going to see that what I mean by this, I'm going to explain this in a moment, but we're going to see that what I mean by this is that the omega, so omega is a 2 form in field space, but what this notation means is that I'm using the vector field delta zeta on field space to eat up that one of the, well, to basically lower the degree in field space, and then now you end up, so basically in field space, both of the sides are going to be 1 forms. So this is why I'm using that notation. Thanks for that. That's a very good question. Okay, so so this is going to be a very useful identity, well known from differential geometry. So okay, so now given this identity, we can now consider the variation of, so previously we have written down a formula for a generic variation of the Lagrangian on field space. Now we can consider a variation of the Lagrangian along a particular vector field, psi, zeta. So on the one hand, I can use this Cartan formula, okay, we have just derived. And this gives me d I zeta L plus I zeta d L. Yeah, so this is from this identity. But now the nice thing about this formula is that the second term actually vanishes because L is a top form. And so we are just left with that. But we also know from the generic, so I could have done the same variation along some vector field zeta that we considered before in terms of the, that gave us the equation of motion and so on. So this would be like from before. So also, it's just different. We're going to now equate both sides. We also know that the variation of L along some vector field zeta is going to be of the form equation of motion dotted into delta phi zeta, right? Now I'm varying with along delta along zeta plus d of this symplectic potential, where one of the arguments is delta zeta of phi. Yeah, so this is exactly the formula that we have written down before. But now I'm just my delta is a derivative along this psi. So now we have, from here, we can see that we actually have an identity, right? So this formula, these two are two different ways to obtain a delta zeta of L. So they must be equal to one another. So in particular, on shell, so on shell, we have an identity, namely that the interior product with zeta of L is equal to, and I'm going to denote on shell by this notation with the like that I've used on the previous board. So this is equal to d theta of delta zeta phi, right? And this tells us that so another way to say it is that there exists basically a let me see. So we can define some form J as the interior product with respect to zeta of L minus theta at delta zeta phi, with the property that dj is equal to 0 on shell, right? This is what we just found. So you can compare and contrast this to the way you usually construct. So if you like rewrite this at, like in coordinates, you're going to get that this J is basically a conserved current. So this is what Noether's theorem usually gives us. But it also means that locally I can, so because of this identity, this means that locally I can find some charge Q such that the J is equal to D of that Q, right? It's true locally, not globally, but so locally J must be exact. So J must be D of some Q of zeta, and it's also equal to this I zeta L minus theta delta zeta, minus theta of the field variations. So this is basically how you, so this is a formula for the charge. You should be able to read it off from the Lagrangian and the symplectic potential in general, and you'd better find that, this expression reorganizes itself into something that's exact. Yeah. Because we have just proved that on shell from this formula, that this identity has to be true. And in particular, that d of j is on shell equal to 0, right? This is what this defining j to be equal to this, d of j comes from here, and since d of j is on shell 0, this means that locally j has to be exact. Yeah.
Related to like the q being a constant in like when you do it less abstract, like here is the d minus 1 form here.
Yes.
Like, how does that relate to like the constant no charge that you get?
Sorry, d actually a d minus. Sorry. So here I'm taking this d minus 2 form in spacetime, not d minus 1. So usually this. So this in ENM, it's going to give you, you can apply this, for example, for ENM, and you're going to find that the Q, well, that for zeta equal to a constant vector, well, in gauge theory, it would be like a constant gauge. In U1 gauge theory, it's going to be a constant gauge parameter, and you'll recover the usual charge.
But where did you use it as a symmetry? Because so far inside the input.
Yeah, but this is actually related more to Noether's actually second theorem, which actually gives you relations between equations of motion. So so far, yeah, that is a good point. Right. Let me think. Let me get back to you about that. Sorry, you're right. In what I'm doing, I don't think I have used that psi with a symmetry. Yeah, that's a good point. But all I have to say is that, yeah, usually in the Noether second theorem, actually, you can consider large gauge, basically like gauge transformations that survive at infinity, and then those end up giving you formulas like this. But yeah. So right. So now, given these charges q zeta, we can derive basically this identity, and I don't expect to have time. Let me just check. We started a little late. Okay, so I'm gonna just in the interest of time, since it's just an exercise that that just uses basically all the formulas that we've written so far on the board and nothing more. Yeah, so to prove this, I'm just gonna tell you what to do. So to prove this identity, sorry, because that was start. Yeah. So what you need to do is to basically consider the following equation. So you take this identity. So I can rewrite that as j minus dq of zeta. Sorry, the j also depends on zeta, so I'm gonna put that label back in here. So this is 0 on shell, so this also means that delta of this on field space also has to be 0, right? Quite trivially. And basically what you want to do now is to just evaluate what this is. So this is going to give us delta J0 minus dQ0 is 0 on shell. And here you're going to substitute for the explicit formula of a J. Do some algebra, and at the end of the day, what you're going to find is that this equation organizes, you can recognize basically in these two terms. On the one hand, this omega evaluated at some change along zeta of phi, delta phi, phi. And then you're going to find another term that's going to be a total derivative on m. So exterior derivative on m acting on delta q zeta minus interior product along zeta of theta delta phi phi. And this has to be 0 on shell because we started off from this formula. So it's just some algebra in between. And I'm happy to discuss if you're interested, and I'm going to post the lecture notes. And you can also find this calculation very explicitly in these notes of Geoffrey Compère. So basically, but this identity is exactly what we wanted, right? So it tells us that there exists a relationship between this two-form omega evaluated along some variation of phi and some quantity that is a total derivative basically of some d minus 2 space-time form kappa, so k. So I can read off from this formula that k along zeta is equal to minus delta q zeta plus I zeta theta delta phi phi plus potentially some other term that is exact on phase space, right? Because here I always have the freedom to add something that's exact. And this thing is very nice. Sorry, let me just put the argument in. The reason why this formula is nice is because it tells us that if I take this d minus 2 form and integrate it over a codimension 2 slice in space-time, I can obtain I can obtain conserved charge. Okay, so provided, so really, okay, let me write down the formula and then I'm going to say a few words. I'm going to say why this is a conserved charge. 1 second. So in particular, this defines for you some flow with respect to psi that is generated by this H. This H, you can think about it as charge associated to psi or some Hamiltonian associated to transformations generated by psi. And this is given by an integral over this codimension 2 slice. I'm going to call this S of k zeta delta phi in phi. So let's just compare a little bit with this formula here. So if I didn't have, if for whatever reason, so first of all, this last term here, the total derivative doesn't matter, because if this thing is closed, then this is going to go away. Now, let's assume for a second that this term involving the interior product of the symplectic the symplectic potential vanishes. Then in that case, you can see that what this formula tells you is that H0, you can integrate it. So then these charges are integrable, integrated in phase space, right, along some path in phase space. And you can obtain H of zeta as an integral of this Q of zeta. And this is the usual Noether charge that one would get. Now, this other term here sometimes can spoil integrability in the sense that there are many situations in which this guy might not be phase space exact. And then you are a little bit in trouble because the charge is not integrable anymore. However, you can go to some place or impose some boundary conditions to make these charges integrable, okay, and hence conserved. So and the slash usually denotes the fact that they may not be integrable, and then we have to impose additional condition to make them so. Okay, so hopefully, so this was just to illustrate the procedure that allows you now to given some vector fields psi that generate some asymptotic symmetries, you can then plug them into this formula that we just derived and compute these charges, and hopefully they're conserved. Or then you can, you know, like you impose boundary conditions to make them conserved, and there are subtleties there, and okay. But for what we're gonna do, I'm gonna explain that around space like infinity, if you impose that fluxes vanish, then these charges will always be conserved. So this is all we're gonna need. And so, okay, we're gonna be interested in GR. So in GR, we can just calculate these things. So first of all, the symplectic potential, you can work it out by varying the Einstein-Hilbert action. So you find that this is minus the determinant, square root of the determinant of the metric G divided by 16 pi G Newton, and then d nu psi mu minus d mu psi mu, where this is the covariant derivative with respect to the metric G mu nu. So now given this, from what we found before, we have that d of Q0 is the interior product along zeta of the Lagrangian form L minus theta. Okay, remember this formula that we've written. But now, because the on shell in gravity, on shell, the action vanishes in absence of any boundary terms. And so you get 0 from the first term, and then you just get the symplectic potential term. And indeed, we find, oh, that's very nice, because when written in form, so this I'm writing it in vector notation, but you can take Hodge star to get the form version of this. And basically you see that this is the d of something, right? The d of a d minus 2 form in space-time. And so it allows you to basically read off So this formula together with this formula, they allow you to read off this Q of zeta in GR. So Q of zeta is minus determinant divided by 16 pi g Newton of d mu psi nu minus d nu psi mu contracted with d minus 2 volume element on this codimension 2 slice, and both of them are antisymmetric, so I can just write these as minus g divided by a pi g Newton d mu psi nu dx mu nu d minus 2. Okay. This is one element that enters in the formula for this cap. I have figured out what this is, and the second one is actually very easy to work out. So it's just the symplectic potential. We've just written it down, so you just have to contract it with this vector field theta. So take the interior product. So the other bit is that I, with respect to zeta of this theta, is just zeta mu theta nu minus zeta nu theta mu of this. And so this is just 2 times zeta mu theta nu d minus 2 x mu nu. And now, so the only other thing, so now we can read off k zeta. So the only other thing, this derive is going to give me something that is going to be now evaluated at an arbitrary variation. The phi's here are going to be the metric, obviously, in this case. So the second term, I'm just going to compute this evaluated at some variation of the metric. And for the first bit, to take this exterior derivative on field space, you need to remember that actually, given this formula for the charge, the covariant derivative, of course, also depends on the metric, and it's going to vary non-trivially with respect to the metric. So you can just find some formula for it. Okay, so it's some exercise, and at the end of the day, and I'm going to conclude with this hour now, you can just write down some formula for this k evaluated at some variation. So let delta phi, delta g mu nu, let's call this h mu nu, then you will find that this k, this codimension 2, this d minus 2 form, evaluated at some arbitrary variation h, and it's also a function of g, the full metric, is, and there is a formula for it. You can derive, as I said, it's just an exercise. So it's d minus 2 x mu nu, and then of course it depends on zeta, and it's going to depend on the covariant derivative on g through the covariant derivative, and it's going to depend on h, which is this variation of the field. So it's something like this, and the indices have to be contracted, and there's a bunch of other terms. So it's not great formula, but it's very explicit. And I hope I don't mess up. Okay. Yeah. So and this h is just the trace of this perturbation. So you can see that now you can just basically take your favorite like well, you can take a solution, so like a solution to the equations of motion in Einstein gravity. You can take it to be a black hole metric. You can take it to be some other metric, an ADS or like whatever. You can plug it in here, and then you can like perturb around that background. Like usually you consider some linear perturbation, and then that will allow you, provided that this perturbation is a symmetry, to construct this conserved charges. And this is what we're going to do in the next hour for basically Einstein gravity in asymptotically flat spacetimes. So the question now that we need is for four-dimensional asymptotically flat spacetimes, what are these zeros, okay? And what are these h's? So once we have those, we're going to be able to write down this object, and we're going to see that they take a very explicit formula, and then we're going to use the conservation of the charges that will follow from this formalism. We'll see in that case that they will also imply the soft graviton theorems. So that is the plan. Okay, so yeah, the plan for the, so now we have basically, can I start? Yeah, we have all of the ingredients to construct asymptotic charges in asymptotically flat spacetimes. So as I said, we need so yeah, so to answer the question from the previous lecture by Sasha, so these psi, if this is a theory of gravity and psi are actually diffeomorphisms, so like linearized, they generate linearized diffeomorphisms, then I think it's more or less guaranteed that the Lagrangian, the usual Lagrangians that we write down are usually diffeomorphism. The action is diffeomorphism invariant. And the stuff that I said actually goes through for these guys. Like if you consider an arbitrary other Lagrangian and consider some other symmetry in fields, some other transformation on field space, it's not guaranteed that the Lagrangian n form is going to transform nicely, like I assumed according to the Lie derivative before. So anyway, so now we are going to, like what we are looking for is some psi's. There are some asymptotic symmetry generators. So there will be some diffeomorphisms that don't fall off to zero at infinity. Once we have these, we'll be able to apply this prescription to construct these charges. So last time we talked about gauge transformations that had like support all the way to infinity. Here we are going to be interested in diffeomorphisms with non-compact support. So we want them to not die off at infinity. And so what are these? So the result is that in four-dimensional asymptotically flat spacetimes, so first of all, these are solutions to Einstein's equations that are given by metrics that fall off or sort of like reduce to Minkowski space at large distances. And naively, what you would expect is that the only, since at infinity we have Minkowski space, naively you would expect that the diffeomorphisms that preserve the form of the metric, sorry, I should say with non-compact support that preserve the form of the metric at infinity, whatever infinity means. So in this case, so in asymptotically flat spacetimes, we have this kind of Penrose diagram. We also drew it before, and we have scri plus and scri minus that are obtained by taking r to infinity for fixed u, or r to infinity for fixed v. So I'm going to do the analysis at scri plus, where again, to remind you, we have coordinates u, r goes to infinity, z, and z bar. So every every point on Scri plus is a sphere parametrized by complex coordinate z. So yeah, so now that we have this condition that we want our metrics to go to Minkowski at infinity, and diffeomorphisms, if these are to be symmetries, then they should preserve this form of the metric. And naively, you would think that for Minkowski space, those are just the symmetries of special relativity, and so you would expect to just get Poincare symmetries. So this turns out not to be the case. So it was shown by Bondi, van der Borg, Metzner, and Cox in the 60s that the asymptotic, so these diffeomorphisms actually, these these vector fields are actually parameterized not by 10 numbers, but rather by functions. So by a function on the sphere, and hence they generate an infinite dimensional symmetry algebra, which is known as the BMS algebra. And later on, Barnick and Trossard so this was only in 2010, they actually also showed that you can further get an enhancement to include vector fields, basically conformal vector fields on the sphere. Sorry, so these are called super translations. So we will discuss them in a bit more detail in a moment. And these are called super rotations, provided that they are holomorphic, that their entries are holomorphic and anti-holomorphic functions respectively. So yeah, so how do we find them? So the idea is that basically what we want to look for is for diffeomorphisms that preserve the metric at infinity. So first of all, what I'm gonna say actually applies to any spacetime. Usually you want to look for some diffeomorphisms that don't fall off to zero at infinity and that preserve the asymptotic form of the metric. So you can also do it in ADS. For example, a famous example is ADS3, where you impose that these diffeomorphisms preserve the pure ADS form of the metric, but then you look for perturbations that fall off, for example, with the real distance near the boundary. So the idea is to look for metrics, so the solutions to Einstein's equations. So here we want these, as r goes to infinity, to reduce to the Minkowski metric plus, roughly speaking, order 1 over r corrections, right, as r goes to infinity. So such that when you take r to infinity, this becomes purely Minkowski metric. And basically, the allowed form of these perturbations is, of course, has to be consistent with Einstein's equation. And it's usually convenient, and this is what Bondi, Metzner, van der Borg, Metzner, and Sachs did, was to first fix a particular gauge. They're interested in studying or really allowing for gravitational radiation to go all the way to infinity. They first fixed the gauge. They wrote down the most general form of the metric with this subject to these boundary conditions in that gauge. They constrain the form of the perturbations by imposing Einstein's equations, and then you find that your metric is then parametrized by some tensor on the sphere, basically. So this is what we are gonna see now. So Bondi gauge is basically 4 conditions on the metric. It's like, roughly speaking, is GRR, GRZ, GRZ bar is equal to 0, and also d by dr of the determinant of the transverse metric is equal to 0. So I'm going to denote by A, B, basically Z and Z bar indices. So metric indices on the sphere. And you can think about physically, basically this tell you that waves propagate radially outwards and wavefronts are spherical and stuff like that, like physical conditions. It's like choosing a coordinate system in which, you know, like waves look nice, the wavefronts are nice. And light rays, I mean, waves propagate radially outwards. So, so this is one condition, and subject to this gauge condition and these boundary conditions that the metric reduces to Minkowski space, you can write it down an ansatz for the metric. So the most general form of the metric is going to be like this. Where essentially all of these functions that appear here, so V, beta, and also this vector field UA, are at this point functions of all the coordinates, UZ, Z bar, and R. So, and GAB, this transverse metric, is taken to be compatible with this condition. So this means that it has to be some of the form R squared gamma AB plus some subleading terms. Yeah, so it's pretty reasonable, and this means that at infinity, this gamma AB tells me what the metric is that I put on the transverse space. So you usually take it to be the metric on the sphere, but you can also work with other basically sections of scry. So you can take it to be the metric on the plane or some other sections basically of the light cone. So sorry, and here turns out that you can consistently impose that the order 1 term vanishes, so the next term goes like 1 over R. And okay, so this is the most general form of the metric, and you can check that this take R to infinity, you get Minkowski space, and that okay, all of these conditions are obeyed, and so far it's just the most general metric that we can write down. And then you impose Einstein equations. And basically, they turn out to just fix. I'm not gonna. It's a pretty simple exercise. You can do it in Mathematica, for example. Take this, put it into the Einstein equation, and expand order by order in 1 over R, and you're gonna start getting constraints between these functions and this vector field on the sphere, or not on the sphere, this vector UA. So, but roughly speaking, everything will be determined in terms of this CAB. and some functions, and a collection of just functions at particular cuts, so functions on the sphere. So so for example, so this beta turns out to just be proportional to CAB times CAB, so that's just entirely given by CAB. This UA turns out to be to leading order in 1 over R to be something like dA CAB, so these guys are entirely determined again by C, but this V turns out to like the GUU, for example, equation turns out to give you a constraint at the leading non-trivial order tells you that du, sorry, so V, I'm writing this as, sorry, V divided by R. So the leading order term here, so the order 1 in GUU is just from Einstein's equations, it's found to be related to the curvature of this gamma. Sorry. So there is nothing new there. So by imposing the radial conditions, you find this like GR mu. Basically, you are going to find this constraint, but then you get order 1 over term that's arbitrary function of u, z, and z bar, and then you further impose GUU to get another constraint on m. So the constraint takes the form time derivative of m is equal to minus 1 over 8 NAB NAB plus 1 over 8 Laplacian on the transverse space acting on the curvature of the transverse space. So reach a scalar and then dA, dB, and AB, and these are covariant derivatives with respect to gamma AB, okay? Not to the full GAB. And what is n here? So n is just given in terms of CAB, it's its time derivative with respect to retarded time. And so we see that as promised, up to a function, an integration constant in u, so a function at a specified value of u, this is just entirely determined by CAB. So this is as promised, and you can do the same for even subleading components in these others. So for example, you can also show, so you can also get the relation on this 1 over R component of GAB. You can also get the relation on the 1 over R component of UA from Einstein's equations. And it's just going to turn out that up to these integration constants in U, these are just given in terms of CAB. So I should say that this is an example of a flux balance law. So it tells you that it tells you what the rate of change is of this parameter m. So m is like, it's sometimes called the Bondi mass aspect, and you see that it's the analog. So if you had the Schwarzschild, for example, space-time, that m would be like the net mass of the black hole. But here you can also have a non-trivial m, for example, if you just have gravitational radiation. And yeah, and it's called the Bondi mass aspect. And the time derivative, roughly speaking, it measures the energy in space-time minus that lost through gravitational radiation. Because as you can see from this equation, the time evolution of m is basically given in terms of this NAB. So first of all, CAB, you should have maybe noticed already, it's like the transverse traceless component of the metric. linear. I mean, it's not linearized in this gauge. It turns out that yeah, it is what it is, and it's like the analog of the of a graviton. So upon quantization, it will become the graviton, and a non-trivial time derivative of this, namely a non-trivial NAB, which is also known as the news. So C is also known as the shear, N is known as the news, and if you have non-trivial news, it means you have non-trivial gravitational radiation. So now you can see from here, for example, if I integrate both sides on the sphere, these two are total derivatives, whereas this one is negative because n squared is basically positive. And so m decreases as a function of time. The integral of m on the sphere decreases as a function of time, and that signals the fact that energy is lost through gravitational radiation. Yes. Oh, sorry, you had a question. Sorry, I thought you had a question. Okay, so yeah, so this is, and it's flux balance law because usually you have the time derivative on the left-hand side, you have the time derivative of a quantity appearing in the metric. It's related to basically something that is a function of this shear and the news. Yeah. How I choose what? So this is just, if you can think about it as a boundary condition. If I want my metric to be the, well, it depends on what coordinates you choose to, what metric, well, what coordinates you choose to express your Minkowski metric in. So you can choose it as, yeah. So what gamma AB is a metric on the transverse space, and it's you can choose that to be whatever you want, and yeah, it's the metric on the sphere or the metric on the plane or the metric on other. So you can like another cut of the light cone. You do have that choice. So yeah, I typically will take it. So the usual choices are this gamma AB be metric on the sphere, and another one is metric on the plane. And the form of the Minkowski metric, I mean, you see it enters, it depends. This guy will change. If I take gamma AB to be the metric on the plane, this R is going to be obviously 0. And then you get some sort of like light cone coordinates in Minkowski space. It's related to the choice of light cone coordinates. If I take this to be the metric on the sphere, it's the more standard choice of like spherical coordinates. Yeah, so it's related to a choice of coordinates. So, okay. Other questions? So basically what we have done so far is to just, we have the most general solution to Einstein's equations. And then now we want to look for diffeomorphisms, so transformations that preserve this form of the metric. So to get, so remember we are looking for this zeta. So to get zeta, we want to look for vector fields parameterized by zeta that preserve the form of the metric as r goes to infinity. And so this means that if I evaluate the derivative with respect to zeta of GUU, for example, I should get something that doesn't touch my Minkowski metric, so it has to fall off as order 1 over r. So my vector fields can act non-trivially on M, but they won't touch this bit, the Minkowski part, okay? And we do the same thing for the other components of the metric. So GUR has to be order 1 over r squared, because it turns out from Einstein's equations that GUR starts at order 1 over r squared and depends on CAB, and this can change CAB, but it's not allowed, again, it's not allowed to change the Minkowski part of the metric. So you can just read off what these boundary conditions are from the metric. So read off the rest from here. Basically demand that ds Minkowski part is unchanged. And so you do this exercise. So this is going to give you like a set of differential equations for I. They're going to be nonlinear in general, but you can solve them order by order in 1 over R because this is what we've been doing anyways. We don't have an exact solution here. And so the solutions are so this asymptotic killing equations if you want. Order by order in 1 over R. And you find that the solutions are as advertised. Function on the sphere d by du plus 1/2 Laplacian on the sphere acting on this function f d by dr plus ya d by dA. And then there is another piece which is 1/2 d dot y u d by du minus r d by dr, and then subleading component. So as I said before, you see like this vector field is parameterized by function f on the sphere and by a vector field ya. The determinant condition turns out to tell you also that ya obeys the following conditions. So as I said before, these are holomorphic and anti-holomorphic vector fields on the sphere, and you can recall that those actually generate Virasoro, 2 copies of a Virasoro centraless, so sort of like centraless Virasoro on the sphere. This is what you would find, for example, when you study conformal symmetries in 2 dimensions. So we have these. In particular, the global components of these. So if you set y z to be 1, z or z squared, and yz bar to be iz bar, and iz bar squared, then you get the usual Lorentz transformations. There are 6 global conformal killing vectors on the sphere, and they generate an SL2C algebra. This SL2C algebra is isomorphic to the Lorentz to SO3, 1. So 6 global ones generate SL2C. This is the same, sorry, algebra, little s, SO3, 1. And right, the other ones are like these, they generate with algebra. And then the other, so this is about these guys with f equal to 0. If you set y to 0 and let f be arbitrary, then you get basically translations. So these are super translations, sorry. So super rotations. The y ones, the ones generated by y are super rotations. The ones generated by these vector fields parametrized by f are called super translations. And you can take this f and you can expand it in spherical harmonics. And if you look at the L equal to 0 and L equal to 1 ones, there's 4 of them, and those correspond to translations. And the rest are basically just other associated to other angle-dependent translations along scry, basically. So for the rest, if you take scry to be the null cone, you can get, sorry, translations with respect to u that are angle-dependent. Yes, at every point, I can shift points on the sphere by different amounts. The translations shift all points by the same amount, usually. So, okay, so now we know. So questions about it? So we have the asymptotic symmetries of four-dimensional asymptotically fed spacetimes. Hopefully it's clear how to, so you should be able, hopefully, to also apply this to other scenarios, theories of gravity as well. It's similar, yeah, it's essentially the same method you'd be using. But now, so this vector field psi give rise to charges of the kind that we have written down before, this kappa of psi. And you can get them like this. Oh, sorry, I have them here. So turns out, so given this psi, you can plug it in to the formula for this kappa h and g, and this h is basically delta g is g minus g0, where this is the Minkowski metric. Okay, so this h is going to be just parameterized by this body mass aspect, by the shear, and so on and so forth. So you plug this into the formula we've written down before, and you find that for super translations, so ya equal to 0, or psi, sorry, zeta equal to f z bar d by du, well, plus the other corrections, we have that delta hf, remember we had the formula, delta hf was an integral over a codimension 2 slice, so here we take it to be the sphere at the path boundary of scry plus, and we get f z bar delta m divided by 4 pi g Newton, provided that there is no flux at this particular cut. So usually you take this to be at u minus infinity. So this is reasonable. So again, remember, if I sort of show this kind of doubled diagram, we have a sphere here on which we are evaluating our charges. So this is a sphere around space like infinity, I0, and you are just imposing that here, so this is a limit when u goes to minus infinity, and you want to impose that basically around this neighborhood of I0, there is no flux. So there is no flux through the spatial boundary, so it's reasonable to assume that NAB is 0 there, in which case you get integrable charges. Notice that they are total derivatives of body mass aspect M. Yeah, and hence they are integrable. And this HF, also called sometimes QF, the generator of super translations, is the integral over the sphere of F times M up to a factor of this 4 pi g Newton. Yeah? And this is called the super translation charge. I should say that for superrotations, and there are many other symmetries, there is a very rich story, and there, subtleties start appearing that I don't want to go into, but I think this formula is more or less unambiguous, and it's been derived in papers by Barnish and collaborators over the past many years, and presumably also by Bondi, although this formalism, this covariant phase space is much newer, of course, than Bondi. So yeah, anyways, so we have these charges. And so now, given these charges, we can see what their implications are on scattering amplitudes. So this was sorry, and the conservation here is really so the conservation really tells you that the charge evaluated on this sphere is related to the one evaluated on this other sphere as v goes to plus infinity. Remember last time we discussed the matching condition. That matching condition turns out to be related to this conservation of these charges as a function of, yeah, time. Minkowski, yeah, my perturbations are h. So h is the difference between the net metric and the Minkowski metric. Because, okay, another way to say it is that my asymptotic.
So the difference between the flat and
When you calculate the charges, you take G0 to be the Minkowski metric and this delta G that has like delta M, delta T, and all of these other parameters in it. You can also take an asymptotically flat background that's parameterized by some non-vanishing C0, for example, like C and maybe some particular value of M, and do perturbations around those. And then, but you are going to get, I mean, nonlinear basically contributions here, but I think this result is, I don't think it depends on what you actually choose that to be. For the linearized, you may get some other corrections here. They're going to be nonlinear. Yeah, no, that's going to be what I'm going to do next. Yeah. So this M is, that this thing is actually secretly nonlinear, but the way the nonlinearity comes in is through the equations of motion. So recall from last time that we said that if we are handed a set of charges that are parameterized by some vector fields, last time they were not vector fields, they were these like gauge parameters that generated gauge transformations in E and M. So we argued that we have some, if we have some matching conditions, so here we can actually understand this as just conservation of this charge around on spatial infinity, on the resolution of spatial infinity. So yeah, there is a way to think about that, them this way as well, and there is an antipodal matching condition that comes in by carefully basically analyzing what happens on the resolution of space like infinity. Let me not really go into it, but the two are related. So we have some matching condition of this form, and we saw last time that you can provided you have this conservation law, you can study what happens. Well, you can look at what happens at the level of the S matrix. And since what you would expect to happen is that these charges should be sort of using the constraints, you can translate this condition into a conservation of the charges in time, and then you can impose that they commute with the S matrix, and then evaluate it between in and out states. So we want to do this for the charges that we found here for supertranslation charges. So what does this correspond to in the case where this is zeta, again, is f d by du. So in this case, we have q of f permitted by f again, is the integral that I'm writing down there, but I can write it as an integral over square plus. Just use Stokes' theorem to write this as integral over the du of m, right? Assuming that, with a minus sign, assuming that m goes to 0 as u goes to plus infinity. Okay? So remember, my charges were defined here, and it's reasonable to assume that at the end of the day, all of my, if you don't have a black hole, in that case, you would have a non-vanishing M at the future null infinity, but let's assume we only have radiation. So if at the end of this gravitational wave event, like the all of the radiation is gone and the mass, this bonding mass has gone to 0, it's an assumption, then we can write the charges that we just derived in this particular way. And then now we can also write the constraints that I've written down before. Remember, the time derivative of m was related to CAB and NAB. So this is the GUU constraint. Sorry, you can also generalize this to GUU is TUU, really. So you can allow for matter as well. But let me just do it for the pure gravity case. So in that case, we get integral, so 1 over 4 pi g Newton, integral over, sorry, and I think there was a sign if you look at the formulas we've written down before. So you get du d squared z, and then f, and then we have 1 over 4 nzz n z bar z bar. I should also say that I'm choosing this gamma AB to be the metric on the plane, so to not carry around covariant derivatives and other factors like that. So just for simplicity, and then we get minus 1 over 4 dz squared n z bar plus Hermitian conjugate. And then in general, we would also have some matter contribution. So let's set that to 0. So yeah, there's basically two terms. So this goes back to Sasha's comments. Like after using the constraint, we get these two contributions, and one of them is linear, and the other one is nonlinear. And notice that this is really an exact, I mean, it's an exact formula for discharges. I haven't really made any approximations here other than this large R expansion. So if you remember from last time, we said that there is a linear piece that is related to insertions of soft photons. So here now we're going to see explicitly that the linear piece is related to an insertion of a soft graviton for a particular choice of f, and that this quadratic piece in n, we're going to also see explicitly that it generates basically like gauge transform, it generates the Lie derivative action on the asymptotic scattering state. And hence the conservation of these charges will be seen to be exactly the same as Weinberg's soft graviton theorem. So this is for Q, sorry, this was Q flat, similar formula for Q minus at F, taking into account this matching condition. And so now let's look at the two components individually. So let's call this, like last time, Q hard being the quadratic in n piece, plus Q soft being the linear piece in n. So let's look at the two components. So let's look at Q soft first. So so how much time do I have left? Let me see. Oh, okay, still quite a bit of time. So let's look at Q soft first. So if you remember from last time, so Q soft, okay, let me write it down, is like minus 1 over 16 pi g Newton, integral over du, integral d squared z, F z squared n z bar plus Hermitian conjugate, right? I'm just copying down this formula. And last time we said that, okay, to understand what this means when inserted to an S matrix element, what we need to do is to sort of quantize this field. And here it's natural because we saw that n is just the time derivative of c. And CAB, we said, is just the transverse traceless component of the metric, and that's naturally associated to linearized, well, to graviton, basically, like to a solution of Einstein's equations that's just a wave. So again, usually you linearize, and this is how you get the transverse traceless component, and then you get gravitational waves from these guys. Here I haven't linearized, but I have expanded at large R. So in principle, the CAB can be like fully nonlinear, but yeah, it still sort of plays the role of a graviton upon quantization. So similar to last time, so last time we wrote down a formula for the gauge field, we expanded it in modes, and we evaluated the large R limit of that. So here we can start with the formula for linearized transverse traceless metric perturbation. We can expand it in modes, and we know that there are 2 degrees of freedom at the end of the day that survive, that are radiative, and these correspond to two helicity gravitons, positive and negative helicity ones. And we have e to the I qx epsilon star mu nu alpha a alpha out plus Hermitian conjugate. Yeah, it's exactly the analog of what we've written down last time, but now we just have like we did polarization tensor associated to the graviton. Instead, we still have 2 helicities. Roughly speaking, in terms of what we had last time, this epsilon mu nu is just epsilon alpha mu epsilon alpha mu in terms of the polarization tensors for the gauge field. It just turns out to be the case. And then for this choice of polarizations. And then RCZZ, just like last time, remember? So this is just like, so if you have G mu nu be G0 mu nu plus kappa, where this is square root of 32 pi G Newton, H mu nu, the CZZ basically corresponds to this H mu, the R times CZZ corresponds to kappa times H mu nu, and it's given by dx, in terms of this H mu nu, is dx mu d by dz, dx mu d by dz, H mu nu. So this means that CZZ is the limit as R goes to infinity of 1 over R times this thing. Yeah, so this is very analogous up to maybe a factor of R is very analogous to what we wrote last time for the gauge field. And after some algebra that invokes the stationary, basically like you now write Q and X, parameterize them like we did last time, take the large R limit, invoke the stationary phase approximation, and you find that this is given by up to some factor that I'm not going to keep track of. We get an integral from 0 to infinity, d omega e to the minus I omega u, a plus out of omega x hat minus e to the I omega u, a minus out dagger omega x hat. So this literally looks exactly the same as before, but now these creation and annihilation operators insert creation and annihilation operators for positive and negative helicity gravitons, respectively. Unlike last time where we had creation and annihilation operators for photons. So this creates positive helicity graviton in the out state. It's create on the, remember this acts on the left on out state, so it creates outgoing gravitons. Similarly, NZZ is just du of CZZ, and basically you just bring down a factor of omega and you flip the sign here. So let me not write it down. But at the end of the day, you see like what enters in the soft charge, right, is an integral over du of dz squared of nzz. So when you perform that integral, so here the only u dependence is in these exponentials. So when you take the, like, again, last time we also did this exercise, when you take the integral over u, so this, remember here, nothing else depends on u but n. So I can rewrite qs as integral over the sphere of f z bar, and then integral over du of dz squared n z bar plus complex conjugate. And I can plug in this formula in here. And the integral over du just gives me a zero mode. So in terms of creation and annihilation operators, you turn out to find that this is limit as omega goes to 0 of integral over the sphere f z bar omega a plus omega x hat plus a minus dagger omega x hat. Yeah? Ah, sorry, I'm missing something here. Like, the derivatives are missing. I need to restore them. I'm integrating this dz squared by parts to hit the f. So this formula I'm writing here is not quite right. Apologies about that. It would be something like this. It would be dz bar squared acting on f multiplying a plus omega x hat plus dz squared of f multiplying a minus dagger omega x hat. So integrate by parts. Okay. Okay, so it's great to have this formula that's linear in the creation and annihilation operators. So, sorry, there's, I also have the other helicity bit. Well, there is another, like I'm looking at the full charge here. So there is actually two components. So it turns out to be the, and I think actually this is, sorry, it's still an, when I integrate by parts, both of them are d by dz bar, right? I'm only doing the first term. I'm doing actually the second term here, because here I have the expansion for nzz. Looking at this term, I integrate by parts and plugging in that formula in there. And then I have to do the same thing for the first term. So both of those come with dz bar squared on f. And now, I guess Pita is here, so let's sort of speed up a little bit. Now, the idea is that if we choose f to be, so f of z bar to be f of z bar minus some arbitrary other, this w is going to be some, you can think about this function as also being parametrized by w, but it's a function of z and z bar. So we take this f to be this. What you find is that dz bar acting on this function basically gives me a delta function. So dz bar squared acting on f is delta function of z minus w. And you now see that in the first term, I'm just projecting onto just a creation, like into an operator that's associated to a photon. And then this, and I'm actually skipping an important bit, which has to do with the fact that this nz bar z bar and nzz are actually related to one another, so that such that these two terms, when you insert them into amplitudes, are actually related to one another. So I'm skipping some step, but at the end of the day, you find that out for this choice of f, out qs s in is just going to be something divided by 16 pi g Newton, limit when omega goes to 0 of 2 pi omega times out a plus omega s in. So I'm also using crossing symmetry to move the photon from in and out states, and I'm using some property of nzz and z bar to combine those two terms into one. So yeah, and there you have to be careful and keep track of all the factors, and it turns out that more or less this looks like 1 over, there may be some coefficient here, but it's like 1 over g Newton times times this insertion of a soft graviton, of a positive helicity graviton in the out state. So this is it's good. This is one piece of the conservation law that has to do with the soft charge. The other piece, it has to do with the hard charge. And last time I promised that, last time I just stated it for these matter currents. I said, okay, matter currents are quadratic in the fields. You can expand them in modes and you can get the required action. So let me do it. Turns out it's very easy to do it quite explicitly for this particular case. So my hard action was something like this. Times f. So this I can use my mode expansion that I found before. So just the du, so nzz is du of czz. So this is going to be integral of du d squared z, and then I have integral d omega integral over d omega prime. So there's two sets of fields. And then we have omega prime, and then we have e to the minus I omega u a plus omega plus Hermitian conjugate times e to the minus I omega prime u a minus the reason why it's a minus here is because I have nzz and nz bar z bar. They correspond to different helicities. When you do the calculation, you notice that's the case. And now the idea is that since both integrals over omega, they go from 0 to infinity, so they're both positive. When you multiply things out, there's going to be 4 terms here, but 2 of them that have both annihilation operators or both creation operators in them, turns out that they will give, the integral over u gives a delta function in omega prime plus omega, and that has to vanish because there is no configuration for which these two can be equal. And so we get, at the end of the day, an integral over the sphere and just one integral over the omega of f, and then we just have a plus dagger plus a minus dagger a minus. There's only 2 terms that survive, and then there is an omega squared. Then the only other thing that you have to do is actually normal order this formula. So and then insert it into this matrix. So the key thing here is that I've rewritten the formula for my hard charge in terms of creation and annihilation operators of gravitons, so I can just use the usual commutation relations of A plus and A, A plus and A dagger plus, and similarly A minus and A minus dagger to compute the action on the asymptotic states. So then we have something like this. You also have to do it for QH acting on the in state, but let me do it for the out state. So here you should think about the out state as basically like, sorry, let me just write down the integral out front, the omega, and then we have omega squared, and then we have the out state consists of a collection of particles of either plus or minus helicity acting on the out state. So these are from out. And then I have to plug in for this QH. So we have A plus omega, A plus dagger of omega plus A minus of omega, A minus dagger of omega, and then S in. And now you basically see what happens. You can just take this and commute it past these guys. Whenever there's a positive helicity thing, this term is going to contribute here. Whenever there's negative helicity operator here, this term is going to contribute. So yeah, so you can just commute A plus minus all the way. Sorry, I'm writing dumb formula. Sorry, it's like this. Yeah, this obvious. I mean, you have to create. Yeah. So it's the dagger that you commuted, and you have this for is equal to 0. Okay, so I'm just commuting the dagger one, and you commute it past, and then you find that each of those brackets. So using the usual canonical commutation relations for these positive and negative helicity gravitons in these omega, z, and z bar coordinates, you can work them out by coordinate transformation. It's a delta function, but let me write it down. So it's like A plus of omega, A plus dagger of omega prime is proportional to up to some factors of pi, 1 over omega, delta omega minus omega prime, delta squared z minus z prime. And similarly for A minus. And yeah, and then you use this here. This allows you to evaluate these integrals over omega and over z. And you find that out QHS in is, again, for this choice of f being z bar minus omega bar divided by z minus omega, the one that we considered before. Well, sorry, for arbitrary f, really, you're going to get the sum over all out particles f evaluated at zk, right? Because if every time this commutes with this guy, I'm going to pick up the corresponding, you're going to get a delta function in z minus zi from here. So we get f evaluated at zk due to those delta functions times omega k, because there is factor of 1 over omega from here, but there's 2 powers of omega from there. And that also gets evaluated at omega k due to the integral over omega. And then we have out S in. Yeah, this is what we get from those 2 terms. And now for F being the choice before, so F of zk was zk bar minus omega w bar divided by zk minus w, right? This is what the function we considered before, and it was parameterized. Remember, by w, we find that this is sum over k out omega k z bar k minus w bar divided by zk minus w, and then out S in. And then you get similar for the other one, for QH acting on in, such that for the commutator, so QH commutator with S, evaluated between in and out state, you get sum over K for all particles. So in and out, omega K, Z bar K minus W divided by ZK minus W, out S in. But this actually, it turns out to be nothing but some, when you rewrite it in terms of the momenta, this is just sum over K, the limit when omega goes to 0 of omega, and then pk mu epsilon mu plus pk nu divided by pk dot, really not, no limit, there is no limit really, but there is a factor of omega, and pk times q. So you see there is like two factors of pk that come with omega k in the numerator, one factor in the denominator. So you have one surviving factor of omega k, and this omega out front cancels the omega that comes with q, and then you can evaluate these inner products and you find exactly what you'll find is exactly this funny factor here, which now putting everything together means that out q s in equal to 0 is equivalent to limit as omega goes to 0 of omega times this object is equal to yeah, so the conservation law that we started off with had two pieces, one that came from the commutator of Q soft with S, the other that came with the, which gave rise to this insertion of a soft graviton, and then the other that came from the action of the hard charge upon the asymptotic states. There is a factor of g Newton, sorry, there that I'm missing. So I think actually the correct formula is some kappa divided by 2. And on the other side, right, on the other side, you get this familiar formula that is just the Weinberg soft factor. So this sort of concludes, I think we have, I hope I have shown you sort of like in a very explicit case, which is this case of pure gravity, how to basically, in principle, you should have the tools now to compute these charges and sort of use this relation between asymptotic fields and their expression in terms of oscillators to sort of like study what the implications are of the conservation of these charges at the level of scattering amplitudes. And we have shown that in this particular case, when we consider supertranslation symmetry and the conservation of the charges associated to supertranslations, we actually end up with the leading Weinberg soft graviton theorem. So with that, I think we can finish and have pizza. Thank you.